For this lesson, which begins our new unit on rational expressions, we're going to take a look at what do we mean by rational expressions, draw a parallel to something that you should be familiar with before, which is a rational number, and we're going to talk about the idea of restrictions. So a rational number, the definition of a rational number is the ratio of two integers where the denominator is not zero. For example, 3/7 is a rational number. The denominator is not zero. If you have a situation where the denominator is zero, you have an undefined rational number. And we've been taught to avoid that. That's usually something we're not allowed to do. A rational expression is just taking this to the next level. Now we're going to talk about the ratio of two polynomials. You've learned a bit about polynomials already. For example, a quadratic equation is an example of a polynomial. So 3x plus 5 over x minus 3, that is a rational expression. I have the ratio of two polynomials. In this case, my polynomials are linear polynomials. Just like with the rational number, we're not allowed to have a denominator of 0. And so we ask ourselves, well, what could cause that denominator to be equal to 0? Is that even possible? And of course, in this case, it is absolutely possible. That occurs when x is equal to 3. If you have the potential for these undefined values where you have division by 0, then you have something known as a whole or an asymptote. And I'll talk about both of those, but the important thing to remember for now is that whatever that value is, it has to be restricted. We're not allowed to go there. Let's continue to illustrate this idea through some examples. Simplify and state any restrictions on this particular rational expression. Now, normally when you think of simplify, you might think expand and simplify, in which case you'd say this expression is already simplified. But for rational expressions, the typical strategy is we need to factor, because what we're trying to identify is whether there are any common factors between the numerator and denominator, which I can then divide out. So in the numerator, I'm going to factor that as much as I can. 2x squared plus 10x has a common factor of 2x, or the greatest common factor of 2x. And then we end up with this additional factor of x plus 5. And then in the denominator, there's a greatest common factor of 3. And then we have another factor of x plus 5. Now, hopefully you can see there are actually two major benefits to factoring like this. One of them is it allows you to identify when you have common factors in the numerator and denominator. I'm going to be able to divide those out. And the second benefit is it becomes much easier to identify the zeros of the denominator. Because just as with quadratics, we were interested in the zeros, we're interested in the zeros here for a different reason. The zeros of the denominator represent where you're not allowed to go. So before I start crossing things out, let's ask ourselves the question, is there any way to turn x plus 5 into 0? And of course, the answer to that is yes. That occurs when x is equal to -5. I could also, you don't normally go this far, but you also have a factor in the denominator there of 3. Well, is there any way that 3 is equal to 0? And of course, the answer to that is no. There is no way for 3 to be equal to 0, so we don't concern ourselves with that as a possible restriction. So now I'm going to divide out those common factors, which is x plus 5. That takes us to our final answer, which is 2x over 3. I need to now, as part of my solution, I was told to state my restrictions, which is that x is not allowed to be -5. Even though I've gotten rid of the x plus 5 from the denominator in the expression, whenever we talk about restrictions, restrictions apply to the original expression. And you need to keep that in mind. So no matter how you may manipulate your expression as you go, we have to consider restrictions throughout the entire pathway. And it can actually even get a little bit more complicated than this. I should say, rather than apply to the original expression, they apply to any form. That's a better way of saying it. They apply to any form of the expression, any stage as you're simplifying, you still have to consider restrictions for it. In this case, because we have lost the information of x plus 5 in the denominator, that means that there is what's known as a hole at x equals negative 5. So this restriction does not represent an asymptote. This restriction represents a hole. And a hole means that the information has gone missing. If we want to find the coordinates of the hole, we sub x equals negative 5. Now, obviously, I can't sub x equals negative 5 into the original expression. I can't sub it into this factored expression, but I can actually sub it into this simplified expression, and I end up with the y coordinate of the hole, which is going to be 2 times negative 5 divided by 3, which is negative 10 over 3. So the hole itself, if you were doing this on a graph, there would be a hole having an x coordinate of negative 5 and a y coordinate at negative 10 over 3. And sometimes I will ask you for that. What are the coordinates of the hole? That means the x and y location. Other times you might just be asked, where is there a hole? And then it's sufficient to just say the hole occurs when x is equal to negative 5. Continuing on with some examples to further illustrate these things. Now I have a quadratic over a quadratic. To factor this, I'm going to have to make use of some different skill sets. Greatest common factor isn't going to do it, although you should always be checking for greatest common factor. In this case, I need two numbers that multiply to positive 6 and add to negative 5. Those numbers are negative 2 and negative 3. And then in the denominator, I have a difference of squares. That's going to be an x minus 2 and an x plus 2. Now, at this point in time, you could, if you wanted to, you could identify your restrictions because everything is visible here. The denominator has this x minus 2 and this x plus 2. We can simplify this by taking out the x minus 2's, by dividing them. And so our final form is x minus 3 over x plus 2. Now, here's where I'm going to start to get very picky and very precise about restrictions. In this final form, x plus 2 is clearly visible. So if you understand restrictions, seeing this x plus 2 in the denominator should tell you that x is not allowed to be negative 2. But this factor of x minus 2 has been divided out of both the numerator and denominator. So in this case, we have to carry forward that restriction that x is not allowed to be positive 2. That's what we get from the factor we divided out. So this piece of information must be included. Okay? The reason we have to include this piece of information is because our simplified form on its own does not tell the whole story. So we need that extra piece of information. Now, the other restriction is that x is not allowed to be negative 2, and that represents a vertical asymptote. And that vertical asymptote is still visible in the simplified expression. And it's a subtle but important difference. Now, if you want to always list your restrictions, that's perfectly fine. But there may be times where you see a simplification and only, or let's say not all restrictions are listed, And it's the subtle difference between a restriction that has been removed from the expression and it's no longer visible versus a restriction that is still present in the expression. And anybody who understands it should automatically realize that that is a restriction. Now, since this x equals -2 is a vertical asymptote, we can see that in that case, x equals 2 must represent the whole. And that's another way to remember this, which is whenever you have a whole, you must include that restriction as you develop your simplified expression. Any vertical asymptotes will still be visible inside the expression itself. All right, we've got another one here. So we've already done this. I'm just reminding you of steps because this looks a little bit different. So we're still going through the same steps that we did before. We're factoring the numerator and denominator separately. We're identifying any restrictions from that factored denominator specifically, and then we'll simplify, dividing out common factors. In this case, a squared minus b squared, that's a difference of squares. That's a minus b times a plus b. Now, this denominator, and this is a situation that does give students a little bit of pause or difficulty. Rather than writing that as b minus a, notice that b minus a and a minus b are awfully similar to each other. And we can actually make them identical to each other with a little bit of manipulation. B minus a, I think you would agree quite readily that that's the same as -a plus b. And then what I'm going to do is I'm going to factor out -1 from both of them, and that turns the -a into a positive a and the positive b into a negative b. So that becomes -a minus b. And now that I've done that, I'm going to be able to simplify. Now, I don't want to lose track, so I'm going to use a highlighter. I don't want to stroke things out, so I'm going to use the highlighter to indicate that I'm dividing out my terms there. Or sorry, factors, not terms. And I'm going to bring this negative sign to the numerator, so it actually just becomes -a plus b all divided by 1. We don't normally write that, of course. You could have gone straight to this, a plus b, or if you wanted to write it as -a minus b, both of those would be perfectly acceptable final answers. But we divided out, and in particular, we created a whole where this factor is equal to 0. So we ask ourselves, what causes a minus b to be equal to 0? And of course, that turns out to just occur when a equals b, which means that our restriction, which we must state as soon as we divide out the factors that make up a whole, we have to state that restriction. If I were being really picky, I would require you to state that restriction with every line, but I will admit that I myself will get a little bit lazy about doing that, especially if there are a lot of restrictions. So I normally state the restriction right away, and then if I do more lines, I will state my restriction with my final answer. Now, in this case, there was only that one extra line, but it's still a distinction worth making. And again, a slightly more difficult factoring problem, not terribly complicated for where you are now. You're in the grade 11 course. You've done a lot of quadratics. A little bit of a hint here. When you see this form, x squared plus xy, y squared, when it's got two variables like that, your factoring is going to be exactly the same as if we had x squared plus x minus 2. The presence of the y doesn't affect things so greatly. What are two numbers that multiply to -2 and add to +1? And that's going to be x plus 2 and x minus 1. And so that means that this numerator, it's going to look very similar in its factored form. It's going to be x plus 2y and x minus 1y, which we just call x minus y. The denominator is going to be y minus x and y plus x, a difference of squares. And just like we did before, hopefully you'll notice that x minus y and y minus x look awfully familiar to each other. And what I'm going to be able to do is I'm going to be able to actually divide those out. But in dividing those out, just like we did before, to make that happen, we actually needed to have a -1. And so another way you can divide those out is then you put the -1, that's what's left over from the division. And so we end up with x plus 2y in the numerator. Y plus x, I'm just going to write that as x plus y in the denominator. And then that whole thing, you could make it so that whole rational expression is just negative by putting the negative sign in front. If you're clear about it, you don't need to have the brackets around it. You could just very clearly put that negative sign in front. But if you're a little sloppy, I do recommend putting brackets there to make sure that it's very clear. This negative sign either goes in front or it goes with the numerator. Traditionally, we don't leave negative factors in the denominator. And now that I've done this, I've lost information about y minus x being equal to 0. That's the factor that I divided out. And of course, that occurs when y equals x or x equals y. I'm going to write it in the x equals form. So x is not allowed to be equal to y. But we also have a visible restriction, and that one is going to be when x is not allowed to be equal to -y. Or I could have just summarized those together and say that x is not equal to plus or minus y. That's also acceptable. You just need to remember to distinguish between these, which is the x not equal to y represents a whole, and the x not equal to -y represents a vertical asymptote. And you'll learn some more about these when you are graphing these rational expressions. So right now, really focus on the idea of restrictions. And then once you get a better feel for what these things look like on the graph, hopefully you'll be more comfortable with them. And for what I believe is our last example now, in the process of simplifying these things, you may end up with two expressions that look the same. But one expression or both expressions might have some sort of restrictions. We determine that two rational expressions are equivalent if they look the same so long as you don't go over the restrictions. So the domain of any expression is the values that are permitted for that expression. So if we're comparing whether or not two expressions are equivalent, we are only comparing them within the domains that are permitted. So let's take a look at expression A, which again is a factored form. Now this one actually does have a common factor to start. The common factor is simply 2. So I take that out, I get x squared minus 2x minus 3, all divided by x minus 1. Notice I don't feel the need to state a restriction yet. Even though there's a restriction present, I don't state that because right now it's still visible in my algebra. Now, two numbers that multiply to -3 and add to -2, that's going to be x minus 3 and x plus 1, if I've done that correctly. And in the denominator, I have x minus 1. So you'll notice that in this case, you probably expected that the x plus 1 and the x minus 1 were going to divide out. But there's nothing saying that that has to happen. So don't make assumptions about these sorts of things. They may or may not actually pan out. So 8x squared minus 2x times 4x minus 1 minus 6. It's probably pretty clear to you that these can't possibly be equivalent expressions. 8x squared, I'll just leave that on its own in front. Negative 2x times 4x is minus 8x squared, so that's going to go away. Then I have 2x times -1 becomes positive 2x, minus 6, and then I have 8x squared minus 8x squared. So this becomes 2x minus 6. If I were going to compare these together, I would factor out the 2, and that would turn into x minus 3. So that being the case, we take a look at these, we recognize that these are not equivalent. So I don't even need to worry about the restriction, but I'll go ahead and write it beside it here, which is that x is not allowed to be 1. So therefore, A and B are not equivalent. And they're really not equivalent in any way, shape, or form. Now, what I think might have been the intent of this example, and maybe I'll even go back and change this note. What if we change A into what I think it was intended to be, which is 2x squared minus 4x minus 6 over x plus 1. The numerator is going to factor to 2 times x minus 3 times x plus 1, all divided by x plus 1. Then I divide out those x plus 1s, and you can see this is a more useful result because now I end up with 2 times x minus 3 with the restriction that x is not allowed to be negative 1. This looks exactly the same as expression B, and since they are the same other than the restriction, but when we're considering equivalence, we don't consider those restrictions. They don't stop us. So under these circumstances, therefore, A and B are equivalent. So I ended up illustrating both ideas. I think the example intended for it to be this x plus 1. So I think I will go and change that in the note. And otherwise, that is it for this particular note. And there's some practice from our current textbook.